Welcome back. So this video is the lecture for Chapter 15. Chapter 15 is about non-parametric tests. I'm going to tell you specifically today about chi-square test for goodness of fit and chi-square test for independence. We'll talk briefly about a couple of other tests that are also labeled as non-parametric and what that means. So yeah, we're going to cover two non-parametric inferential statistical tests. Here are a handful of symbols we're going to use. O is for an observed value. E, the expected value under the null hypothesis. Our summation sign. This funky looking X kind of thing is called chi, so chi-square test statistic. Degrees of freedom, of course, and these are familiar. Null hypothesis, independent variable, so it's the one a researcher manipulates, and dependent variable, the one a researcher measures. A quick note, I'm not going to go super slow right now because you can, in YouTube, where I've posted this, you can adjust the speed at which it plays. So if you need it to be slower or just prefer that, then you can do that. Let's take a quick zoom back in time to a day early on in the semester where we discussed scales of measurement. This is one of the first things we talked about in this class, or pretty early on. So what we mean by this is when we look at a dependent variable, the thing we are measuring, a variable can vary in a few different ways. So a variable can be nominal, so simply categories or names of things, like names of universities, for example, or ordinal, so ranking, first, second, third place interval, where it's ranked in some sort of order, but the intervals are also equally spaced. And ratio, where it has all those features of interval, but also a meaningful zero. And all the tests we've worked through for most of this semester, everything we've covered so far, are paired with research designs where the dependent variable is either interval or ratio, what we have been calling scale variables. And so when we want, and those types of tests are called parametric inferential tests. So when we are comparing samples, for example, like a sample to a population that we know, so a z-test, or when we, or a sample to a population we know, like in a t-test, or in a t-test with two groups that are between subjects, we compare those groups and compare them on some variable that is either interval or ratio. If we have, say, for example, one independent variable with 3 or more levels, or 2 or more independent variables, so we run ANOVA. In all of those cases where the dependent variable is interval or ratio, those are the tests we use. If we're thinking about how two variables are associated with one another, when both of those variables are interval or ratio, we use correlation or regression. We've talked already about correlation, and we'll talk on Tuesday about regression. But what do we do if our dependent variable is nominal or ordinal? We can use tests called non-parametric tests. And those tests, we'll cover a couple of them. We're going to focus on chi-square tests, where the dependent variable is nominal. And I'll describe at the end a few tests where a dependent variable is ordinal, for example. And if we're looking at association, there's also correlation, a correlation coefficient that we can use when the variables that we want to associate to each other are ordinal. So what does it mean for a test to be non-parametric? So we can apply them to those situations, but they're kind of different from parametric tests in one more way that's important. So when the assumptions for parametric tests are not met, specifically when one of these three things happens. When the dependent variable is nominal, when it's ordinal, or when the sample size is small, like 10 or under 30 generally, or we suspect the underlying population is non-normal. So a case where we would be, where we really shouldn't use, say, a t-test, for example, would be if we had a sample of 10 and we had reason to believe that the population normal or population distribution is actually skewed. Now, if we had a sample, a very large sample, even if we thought the population distribution is skewed, a very large sample is going to make the comparison distribution more normal, and so we could still apply a t-test. So these are three situations where we would use a non-parametric test. So non-parametric tests don't rely on the same assumptions as parametric tests. And remember, assumptions of the parametric tests are essentially the ideal conditions that we need to meet to be able to use those tests. And sometimes when we violate those conditions too harshly, we have to use non-parametric tests. There are some disadvantages to using non-parametric tests. For one thing, we can't always calculate confidence intervals or effect sizes, although I'll show you one effect size measure for chi-square that we'll work through today. And also, they tend to have lower power than parametric tests. In other words, we have a higher probability of making a type 2 error when we use non-parametric tests versus parametric tests. So they're not as good at detecting real effects. But sometimes we have to use them. So let's move to one. Chi-square tests are what we're going to focus most of this lecture on. And I'll tell you about two different types of these. The basic idea here for both of them is how different are the observed values from values expected given the null hypothesis. So there are two types of these. One is the chi-square test for goodness of fit. And so it's the goodness of fit to the null hypothesis. How well do the observed data fit to the expected data? We use this when we have just one nominal variable. There's no independent variable or dependent variable. It's just one variable on which individuals are placed into two or more categories. And I think that'll make more sense in a moment when I give you the example. And the idea is we see if our data, our observations, fit some theoretical expectation, what you think should happen if all were equal. And the second test we'll cover is the chi-square test for independence. In this case, we have two nominal variables. And we want to see if they are related in any way or independent of each other. So we don't need to designate one as an IV and a DV, but it's often useful to do so. And in the example we're going to work through, it'll be clear that we can pick one and call it the IV and treat the other as the DV. So again, we want to see if they're independent or if they're related. Let's start with the chi-square test for goodness of fit. So the chi-square test for goodness of fit to the null hypothesis. Let's use this example. Say we're going to flip a coin 100 times. And the null hypothesis is that it's a fair coin. And so we should get heads 50 times and tails 50 times. And so we can make a little table showing the expected values under the null hypothesis. So our table off to the right here, what we're going to plot in here is if we flip a coin 100 times, we would expect 50 to come up as heads and 50 to come up as tails. Now we know though, if we actually flipped a coin 100 times, even a fair coin is probably not going to actually come up 50 heads and 50 tails. It'll come up maybe 51 heads and 49 tails or something like that. But in the long run, the expected probability here, the expected values here are 50 of each. So if we were to flip the coin 100 times, and what we actually get are these values, that we got 58 heads and 42 tails. Notice, of course, those add up to 100. Then our question is, well, was this a fair coin? The idea is, are these observations a very low probability event if the coin were fair. So are they far enough from the expected values for us to think, well, the coin must actually be not a fair coin, some sort of trick coin? So how do we test for that? We're going to use the chi-square statistic, and it has this formula. So it's the summation of some deviations over the expected value. So it's deviations of the observed value from the expected value, square that, over the expected value, and we sum that up for all categories in the variable. In this case, there's only 2 categories, but there could be more. So let's look at that example and do the math here. So here's a table you could use to perform this test. So we have our observed frequency. There were 58 heads, and the expected frequency was 50. Our observed frequency for tails, 42, and 50 for the expected frequency. So observed minus expected is simply 58 minus 50. We have 8. Or 42 minus 50, we have negative 8. Now we square each of those, and of course they'll come out the same. And we take that value and divide it by the expected frequency of 50. So 64 divided by 50 is 1.28. And now we just sum those. And that's our chi-square. So our chi-square is 2.56. But what do we do with that? Well, we have to have a critical cutoff value, right? So this is the same process we've used over and over again, where we are calculating a test statistic and we're going to compare that to a critical cutoff value. If it's more extreme than that critical cutoff value, we reject the null hypothesis. So how do we get our critical cutoff value? Well, like many of our tests, we calculated degrees of freedom. In this case, degrees of freedom is simply the number of categories. In this case, 2, we have heads and tails. We could have other cases where for one nominal variable, there are more than 2 categories, but here there are only 2. So k minus 1, so our degrees of freedom is 1. And now we have a chi-square table. You have this in your textbook. This is a small excerpt from that. And so let's say we use alpha of 0.05 and degrees of freedom 1, we're going to have a critical cutoff value of 3.841. Here is a chi-square distribution, the sampling distribution, also known, right, as our comparison distribution, under the null hypothesis with degrees of freedom of 1. Our critical cutoff point determines what portion of that or where on that distribution 5% of the distribution is more extreme than. And we ask ourselves, does our test statistic fall into that rejection region? And in this case, it does not. It's less extreme than our critical cutoff value. So we fail to reject the null hypothesis. This seems to be a fair coin. In other words, even though these values deviate from the expected frequency, they don't deviate enough for us to think that this is not a fair coin. The probability of getting 58 heads and 42 tails is relatively high. It's somewhere over here in the distribution. But let's look at one more example. Let's say we have this weird coin up here. I don't know where this coin is from or whatever, but let's say that we're unsure of whether this is a fair coin. You've never encountered this before maybe and you're not sure. So let's try flipping this coin 100 times. And now you might pause the video and fill in the table, because I'm going to pop up the values in here in just a moment. I'm not going to pause. You can pause. Okay, if you paused, here's what you would have produced in that table. So 62 minus 50 and 38 minus 50, we have 12 and negative 12. We square each of those. We divide 144 by the expected value, 50, and we get 2.88. We add those two, and our chi-squared this time is 5.76. We had the same degrees of freedom because, again, we just had 2 categories. And so that means we had the same critical cutoff value. But this time, our chi-square is more extreme than our critical cutoff value. It's in the rejection region, so this time we reject the null hypothesis. It seems like this coin is not fair. In other words, getting 62 heads and 38 tails in 100 flips is a pretty low probability set of observations if the coin was fair. It's too far from our expected frequency for us to think this is actually coming from a fair coin. So that's the chi-square test for goodness of fit. Let's move on to the second type, the chi-square test for independence. We use this when we have two nominal variables. I'm going to pause for a second, not pause the video, but I'm going to come back to this in just a second. I mentioned briefly, but let's say again, we could have a nominal variable that has more than two levels. For example, we could have something like, we ask 100 professors at WashU, what's your favorite class? Freshmen, sophomore, juniors, or seniors? So every professor out of the 100 asked has to vote for one of them. Now, if it turns out that freshmen, sophomore, juniors, and seniors are sort of equally likable, then we would have 25 professors who vote for each one of them. So 25 professors would say freshmen, 25 would say sophomore, 25 would say juniors, and 25 would say seniors. But if we were to actually get some data, we might find that, say, freshmen and sophomores get more votes than juniors and seniors, or vice versa, who knows. But we can run this same chi-square goodness of fit on a nominal variable like that with more than two levels. So that would just change things just a little bit. Okay, let's talk now about the chi-square test for independence. So this one is used when we have two nominal variables. And like I said before, we don't necessarily need to designate an independent variable and a dependent variable. It sort of depends on the situation. But let's look at, in an example, what we would do there. So again, the kind of idea behind this one is whether two nominal variables are independent or are they related. So the example, one example given in the book, and no joke about this, is that the question behind this research was, does entertainment by a medical clown, by a clown, influence the success of in vitro fertilization? So the idea behind this, and this is real research published in 2011, the idea behind this, there was a medical doctor, Friedler, maybe it's pronounced Friedler, who, before he became a medical doctor, had attended a mime school in France. He knew that fertility patients were stressed out by the process of in vitro fertilization. I mean, so these are people who oftentimes attempted to conceive by other means first. That didn't work. Then they go through the process of starting in vitro fertilization. It's expensive. It's a lot of things that are stressful. And it turns out that the stress level during the embryo transfer phase, when the stress level of the potential mother-to-be influences how likely that person is to get pregnant. And so a mother who's really stressed out actually has a lower chance of that embryo kind of taking hold and for conception to happen there then. So this doctor said, okay, stress is bad for this process and laughing lowers stress. So let's make clowns make the potential mothers-to-be laugh during this process and see if that affects pregnancy rates. So an interesting question, kind of an important one too. So the idea here, what we're going to call the independent variable, is whether there is a clown or not during the embryo transfer phase of in vitro fertilization. So yeah, they have some clown come in and for 12 to 15 minutes entertain the woman during this process or right after the process or something like that. So in this, let's say there were 110 women entertained by the clown right after the embryo transfer, so not like during the actual thing, but right afterwards. It's an important phase of all this. And then there were 109 women in a no clown control group who just went through the normal kind of steps of this and no clown came in. And the dependent variable here, what we're going to call the dependent variable, and appropriately so, is whether or not woman becomes pregnant after this process of in vitro fertilization and the embryo transfer that's part of that. So what makes this different from, say, why we can't use a t-test though, right, is that the dependent variable is nominal. Because this independent variable, we could assign people into the clown or no clown levels of this independent variable. And that could, if we had a different dependent variable, like if we measured whether stress goes down as a consequence, well, that dependent variable, we could use a t-test to find out if stress differed based on whether there was a clown or not. But the dependent variable of pregnancy is nominal. Someone's either pregnant or they're not. There's not sort of a more or less pregnant, right? So the null hypothesis here is that pregnancy rate is independent of whether or not there was a clown. In other words, it wouldn't matter whether a clown came in and tried to make the woman laugh or not. Pregnancy rate is what it is, and the clown's presence or absence doesn't matter. So here are the observed values from this study we're going to walk through for our example at least. And so the way this table is set up, this column is how many women out of all the women in this study got pregnant and how many did not get pregnant. And that's set up by whether there was a clown who came in to try to make them laugh or whether no clown ever showed up. And so for example, this 40 here is the number of women who ended up becoming pregnant after seeing a clown make them laugh during this process. And this 22 is the number of women who got pregnant without a clown being there. So we're going to end up using chi-square, and it has the same formula as before. But it's a little trickier this time than in the test for goodness of fit. This time we need to get expected values for all 4 cells, the clown, the women who got pregnant when there was a clown, women who didn't get pregnant when there was a clown, and so forth. We have to do it for all 4 values, and it's a little trickier to calculate that compared to the goodness of fit. So we'll do that now. But first, let me just briefly tell you, I'm using slightly different values than the ones in the text. These, in this table up top, are the values that the textbook gives you for this example problem, but I found it to be kind of confusing because the clown versus no clown categories ended up with the same number of observations. They both had 93 women, and I think that's right. Yeah, and it turns out that I think that's just harder to follow the math and be 100% sure about what's going on. So I'm going to use slightly different values than those in the text, but the outcomes are the same. And one other super small note, if you were following along doing this in the textbook and you got to page, I think it was like 442, you saw this table and you might have noticed there's a typo. So these values in the middle over here, this 27.518, for example, is not the observed minus expected for this row. They should drop that 2 off the front. So weird typo, but I wanted to make sure if somebody's sitting there going, I'm so confused, why is that? That's not how math works. You're right, so there's a typo in the text. Moving on, back to our problem, clowns and pregnancy, yay. So the chi-square test for independence here. Here's how we do this. We take our observed values. We're gonna produce expected values based on our observed values. So to do this, we start by calculating row totals. So we add 40 plus 70 to get 110. That means there are 110 women who had a clown come in and try to make them laugh right after embryo transfer. And we do the same thing in the no clown row. 22 plus 87 is 109. I don't know if you can hear that, but my baby's crying. Sorry. Okay, so then we also want to calculate the column totals. So uh, for we want to know how many women altogether ended up pregnant from this process, and we add 40 to 22, and we get 62. And finally, we do the same thing for how many women altogether did not get pregnant through this process, and it was 157. So a quick note, this is not the same thing as what we did for a 2x2 ANOVA, where we had a table that looked a lot like this for two independent variables, and we had placed the dependent variable measures in these cells, and then we, in that case, took averages and called them marginal means. This is not the same thing. This is a different process, even though it looks kind of the same. If you take the average of these, you are going to get everything else wrong. So remember, these are totals where we add those up. So 40 plus 70 is 110. So not the average. Not the average. Okay. What do we do with those? First, we add those up. You could either add 110 to 109 or 62 plus 157. Either way, you're going to get a total of 219. There are 219 people. That's also if you added all four of these numbers together, right? So there are 219 people in this study. And that's going to help us calculate the expected value in each cell. We use this formula. The expected value is the total of a column over n, the total of everybody who was in the study, or all the observations, and multiply that by the total of a row. So let's start with how many women ended up getting pregnant after they had a clown try to entertain them. So let's take 62, the total for the column of all the women who got pregnant. Divide that by the total number of people in this study, or total number of observations. And by the way, that's 28%. That's just a quick side note, right? Is 62 out of 219 women. So the only 28% of women who went through this got pregnant altogether, right? So that's not a super successful procedure overall, regardless of whether there was a clown or not. But okay, so now we take the total number of women who had a clown try to entertain them and pop that into here. And that's our expected value for what we should expect if the clown and pregnancy variables are not related to each other. This is what we would expect, is 31.14. And we would do the same thing for the other three. So for the no clown, we would take 62 again, but this time 109 would be what we plug into here, and we get 30.86. And we would do it for the other two as well. So we do that for all four expected values. And now we have to take those and plug those into this formula. So one at a time, we take the observed value minus the expected value for that same cell, divided by the expected value by that same cell. Sorry, I skipped a step, and don't skip this step. So observed value minus expected value, square that, and then divide by the expected value. And we would get 2.52. And we hold on to that for a moment, because then we're going to do that same thing for the other four cells, and where I've placed these correspond to where they're placed in the table. So we do that for all four. Observed minus expected, square over expected. And to get chi-square, we add those four up, and that's our chi-square. What's the critical cutoff value? Again, we need a degrees of freedom. This time, it's the degrees of freedom for the rows times the degrees of freedom for the columns. K is the number of categories. So here we have two categories, clown and no clown. So 2 minus 1. And then two categories here, got pregnant, didn't get pregnant, 2 minus 1. So we multiply those by each other, and we get 1. So we can use that same table we used in the last problem. And again, using an alpha of 0.05, it turns out we're going to get the same value here as what we used before as our critical cutoff. So our sampling or comparison distribution under the null hypothesis with the degrees of freedom of 1 looks like this. Our chi-square is way off into that tail, so we're going to reject the null hypothesis. Pregnancy rates do appear to be dependent on whether or not women were entertained by a clown post-IVF. So it turns out women are more likely, it seems, to get pregnant when a clown is around than when they are not. A strange but true occurrence as published in a real science journal. Okay, so one more note is, again, we could have more than 2 levels of each of these nominal variables, more than 2 categories. In this case, for the pregnancy one, we really couldn't. It's either got pregnant or didn't. The clown one, perhaps we could have like a really funny clown, a scary clown, and no clown, and we could see which one has the biggest effect on whether women get pregnant. I don't think we'd want to do that. We'd probably have some ethical problems with that. But in concept, you can run a chi-square for independence test when one or both of the nominal variables has more than 2 categories. All right, so what about effect size for chi-square? Effect size for chi-square is called Cramer's phi. It has this weird V symbol. And this is how you calculate it. You take chi-square, so in our case we had just calculated 7.06. You divide that by the product of the number of observations altogether. So we had 219 women in this study, times the degrees of freedom total. So that's the row by the column. So then we take the square root of that whole thing. And this is Cramer's phi for this study, 0.18. But is that big, medium, small? Here's the table for that. So in this case, it depends on whether there are the degrees of freedom total is 1, 2, 3, and ours was 1. So this phi of 0.18 is somewhere between a small and medium effect. It's kind of midway between. So it's a small to medium effect. In other words, if you know somebody who is attempting to conceive with in vitro fertilization, and they're like, hey, my hospital wants to charge us an extra $20,000 for a clown to come in and try to make me laugh for 15 minutes. Is it worth it? You might say, well, I don't know. That's a lot of money for a small effect size. That's not likely to have a huge impact on things. But at least we know it does potentially have an impact. But it's not a big effect. All right, so I've said this a couple times, but all the examples we've looked at so far have had only 2 categories per variable, but we could do both types of chi-square test with any number of categories per variable. It doesn't have to be the same number of categories per variable in the chi-square test for independence. It could be, like I was saying, with pregnancy would be pregnant or not, so 2 categories in that variable. And the clown one could be like entertaining clown, scary clown, and no clown. So the other variable could have more categories. That's possible. All right, and then the last thing for this lecture, this table tells us a bit more about a few other non-parametric tests, and in the book it goes over a few of these tests. But let me just kind of orient you to what this table is doing. So for each parametric test, so for each of these different designs, where, for example, we're interested in the association between 2 variables. If those 2 variables are both either interval or ratio, then we can use a parametric test, a Pearson correlation coefficient. And that's what we covered in our lecture on chapter 13 on correlation. But if one or both of those is an ordinal variable, then we would use what's called a Spearman rank order correlation coefficient. And the process for that is just a little bit different. Now let's think about designs where we have 2 groups and it's a within groups design. In other words, it's actually one group of people that go through 2 things. And we want to compare them to each other, basically. Well, if our dependent variable, the thing we're interested in measuring behavior on, is scale, so interval or ratio, we use a paired samples t-test. But if it's ordinal, then we would use what's called the Wilcoxon sign rank test. And just And similar, if we had a between groups design where it's two groups, we would use an independent samples t-test if it's a ratio or interval dependent variable. But if that dependent variable is ordinal, we use what's called the Mann-Whitney U-test. Finally, if we have, say, one independent variable with 3 or more levels and it's between groups, you learned earlier how to do a one-way between groups ANOVA when that dependent variable was either interval or ratio, when it was a scale measurement, scale dependent variable. So a parametric test. The non-parametric kind of counterpart to that is the Kruskal-Wallis H test. So the book covers a few of these. We will not on the exam ask you to calculate these, but we may ask you questions about them, particularly about when you would use them, but maybe some other questions that would tell us whether you actually read and worked on trying to understand those from the textbook. Okay, so that's the lecture on non-parametric tests. I will try to carve out a few minutes during lecture on Tuesday for questions about these things. And we'll have some extra office hours too to make sure that everybody's ready for the exam on Thursday. Thanks a lot and enjoy the rest of your weekend.